Alright, this is a video for a request on the student room. Now, turn the top on. Line what it is. There you go. Right, so a bit better. Yeah. So yeah, as I said, this is a request. So anyone else just go and watching. You've said you want to do a video on stationary waves in a node where there's nodes and antinodes. So what I'm going to do in this video for you, Lucent, if that's your name, what we're going to be doing obviously is demonstrate inside a tube. And first of all, what I'm going to do is demonstrate. I have done another video, but just to summarise it, I'll do sort of a stationary wave, how it's formed, and I'll just show sort of how it's formed inside tubes, which is same thing if I think I'm following my train of thought correctly here. So the first thing we need to do is draw a sort of a baseline for the wave. So if this is, say that is your baseline there, I've drawn on the board. Let's just see if you can see it. Yeah. So you can, big red line across the screen. So basically, what we've got here, in one colour, in red, this is going to be our first progressive wave. So a progressive wave, and now that has got a wavelength of one lot of this. So it is it's a first overtone, as there's a whole wavelength there. So it's a progressive wave. So that's sort of the kickstart to it, really. Just you find where the pen that we are. And this is the other wave. Same amplitude, same sort of phase difference. It's 180 degrees out of phase. So this one is going, black one is going this way. So I put like an arrow on it, and the red one is going the other way. Now, bearing in mind, for two progressive waves to form nodes and antinodes, they need to be 180 degrees out of phase. What this means is the phase difference is 1 pi, 1 radian pi, if that's what you want to call it. And this is so that they intersect and they form super troughs and super nodes, or whatever you want to call it, super crests even, and super troughs. So this is a super crest at the top, and that's a super trough. Now, if a node is where there's no displacement, so this is a node here, so it's where they intersect on, so this stationary, two progressive waves form a stationary wave, which just looks like a straight line. But to emphasise it to you, what I'm doing is I'm sort of demonstrating how that stationary wave at the bottom comes about. Because if I just drew that straight line, you wouldn't know what I'm on about. So, damn it, that's rubber. So, what I've done there is there's two stationary waves, and there's a node there. That's why there's no displacement. And when we mean no displacement, it's not above the line. Basically, this line represents like the string, if you can imagine it. And these are vibrations, and you can't actually see it. It's so fast, it appears like there's a straight line. That's what might have confused you there. So a node is where there's no displacement. So this is a node. Now, the opposite of having no displacement is a maximum displacement, and that's what we mean by an antinode. So an antinode is the same as the amplitude of the wave, and because it's the same on either side, it's basically just the amplitude, the height of one crest, so to speak. So that's why we form the antinode between the top and the bottom of the wave, if you want to call it that. So that's one complete cycle there of each thing, and we've got an antinode at the maximum amplitude. So that's what an antinode is. You just sort of demonstrate that there. So I'll sort of point it with my finger if I can. So the top of the wave there, when it reaches the top of the wave, that's an antinode, and that's a node. You just remember that the antinode is the opposite of the node. That's why we've got the word anti in front of it. So that's kind of why that happens. I mean, you could have like a second overtone, third overtone on there, but for simplicity, I've just drawn a simple first overtone, because a fundamental just includes half a wavelength, and that won't be sufficient for what I'm trying to demonstrate here. not sure what more you want me to add to this video, but just for to cover all bases, I'm going to show you so you can rub this off. Just in case you don't know what I mean by phase difference. Oh, actually, no, I think a better way of doing it. So, yeah, before we do the calculation for phase difference, there is a calculation which is in my book somewhere, I think. Just give me a second. Just leave the board for a minute. I do have it somewhere. Just have to. Right. Okay. So sad that I'll find it in a minute. Right. Okay. So you've got that. You remember that wave I was just mentioning before. So it looks something like this. So a wave is not. It's not a continuous line because, as we know, you could see it as a particle thing because of wave-particle duality, which is more a Unit 1 topic, but I'm gonna make it sort of a Unit 2. So that wave, this here, what I've just drawn there, is exactly the same as this. Them two are exactly equal to each other. This line just represents these particles moving. That's why we call it wave-particle duality, because they act as one complete sort of wave thing together. So they interact, and now if I draw it to make it look like the wave we had before, so I think it was something like this, what we had before. I know the colours are reversed, but it looks something like that. So as you can probably tell, it's going to look something like this. Now, when I was talking about the phase difference, if you look it up in your book, is the difference between two adjacent vibrating particles. Now, what we mean by that is two particles that are sort of opposite, but in the same sort of line as each other. So the first particle vibrates with the first particle of the second wave 180 degrees out of phase. So these two, I don't know if you can see what I'm pointing at here. I'll zoom in actually. Make it a bit simpler. The first two particles there, they are 180 degrees out of phase. The second two, them two, are 180 degrees out of phase. That's why, so each particle with its adjacent one is 180 degrees out of phase. That's why they sort of construct and destructively interfere at these points. So constructively interfere is when they create a super trough, so they go up together, so they push each other up. However, a supercrest is when they do the opposite, when they push each other down, because it's sort of the force of both going up adjacently. So I don't know if that clarifies anything you weren't sure about. We're going to put the antinode and node there. So we've got the antinode here, get AN, and all I'm doing is zooming this bit out to corresponding N there and anti-N. So these two are exactly the same wavelength, same. So this I'm just going to call it lambda. I'm not 100% sure if you want me to do speed of waves, how you calculate that. I'm assuming you know a little bit about the speed of waves and stuff. I mean, you just quoted nodes and antinodes there. Not sure sort of what more you want me to do, if I've covered everything. Go on, I'll just pause the video and I'll try and find that book. Sorry, just went off to try and find the book and I've got it. What I'm going to do now is I'm just going to go through the AQA book, and I'm going to help you some more with if there's any more bits I've missed out. Just going to see. I talked about the stationary waves, talked about the nodes, polarization. Do you do that? Do that in a minute actually. And I have done all these videos before. So just looking for the main equation there. I've got it. So two adjacent vibrating particles have a phase difference. Now the phase difference is calculated by a phase difference. I won't put PD because that's confusing, as there's no potential difference. I'm just going to put P. And the equation is 2 pi d over lambda. 2 pi d over lambda. Now you may be looking at me going, right, well, first of all, what is pi? Well, that is just pi, a value, normal. D is a distance between the two adjacent vibrating particles, I think, is it? No, this D, so this D here is a distance along the wavelength. So this could be D. If you picked this particle here, it'd have D of this, that'd be its D. And then you've got the wavelength which goes all across. And so basically it's sort of a ratio times by 2 pi of the wavelength of the phase difference. And you can measure the phase difference of one wave to another, and you take it away and you've got the phase difference between the two. Hopefully that's kind of a summed up phase difference for you if you didn't know that. Some more sort of key terms. So displacement of a vibrating particle is known as its distance and displacement relative to its equilibrium position. Amplitude is the maximum displacement of a vibrating particle. So what we were talking about is like this one here. So that's the maximum distance there, as it doesn't get any higher, assuming D is the same for this particle down here. Assuming that is exactly the same for that one. Period of a wave is the time it takes for one wave to complete a whole cycle, and that's the same as 1 over the frequency, and you can just swap frequency and the other one round. We talked about supercrafts, stationary waves, we talked about that. Not sure if you know this, but cover it anyway. So I will go over just sort of the stationary waves on strings, so the second, first and third. Oh, I'm not sure if you should do that or not. It's just basically F equals C equals F lambda, and F equals C over lambda, and you rearrange that to get the speed of each wave, the fundamental overtone and stuff. I'm not sure. I think I've covered everything. Polarization waves is where transverse waves operate on the horizontal and vertical, whereas longitudinal waves only operate in horizontal. So transverse waves are the only ones that can be polarized. Polarized waves, so an unpolarized wave might look like sort of many arrows, sort of like that. So it might look something like that at the top left, right there. Just to see if you can, have to be quite quick here. So an unpolarized wave might look like that, and then you might get a polarized wave that goes through a filter and just ends up looking something like that. Only operating on one plane at the top. Oh, it's a bit out of shot there. So the polarized wave only operates on one shot there, and that's when it's gone through a polarized filter, which is useful for sunglasses. Now, that was a quick overview, and I've sort of focused on what you wanted me to focus on. Hopefully that's kind of helped you somehow. If it hasn't, just drop a link and I'll surely respond as quick as I can to you. Whatever you send, personal message. Yeah, hopefully that sort of clarified a few things for you. Just give us another shout if you haven't, obviously. We'll see you in the next video.